3.7, Proving Segment Relationships. So upon completion of today's lesson, you should be able to write proofs involving segment addition and write proofs involving segment congruence. So we have two postulates we're going to talk about today. Postulate 2.8, which is the ruler postulate. It states that 2 points on any line or line segment can be put in a one-to-one correspondence with real numbers, meaning that if you use a ruler, you can basically measure the distance starting at 0 of any line segment. The key one for today is going to come from 2.9, and it's going to tell us that this is the segment addition postulate. We've talked about this before this year, where the sum of the parts is equal to the whole line. So if A, B, and C are collinear, then points B is between A and C if and only if AB plus BC is equal to AC. So now what we're going to do is we're going to use this concept of the sum of the parts is equal to the whole, and we are going to apply it here in our first example. If you remember, everything we're going to do now is in a two-column proof. And so it says prove that if CE is congruent to FE and ED is congruent to EG, those two pieces of information, that is my given information. And then it's asking us to prove that we know that CD is congruent to FG. So anytime you start with a two-column proof, you always are going to draw your T-table, and you're going to have your statements and your reasons. So anytime we have a two-column proof, step one is always the given. So step one says that we have CD is congruent to line segment FE, and we have line segment ED is congruent to line segment EG. And again, that information is given. So then we go to step two. And in step two, we have to talk about definition of congruency. And when we use definition of congruency, we are going to get rid of our congruent sign as well as our line segments, because we're talking about distance now. So we are going to make step two is going to say that CD is now equal to the distance of FE. We also now know that ED is equal to EG. And in that step, that is definition of congruence. So then we get into step three. Now this is where we're going to use our segment addition postulate. In step three, when we start using our segment addition postulate, what we are going to do is we want to talk about one of the two lines. It doesn't matter which one of the two lines we talk about, the distance from C to D or F to G. I'm going to start by talking about the distance from C to D. So step three, the whole line is equal to the sum of the parts. So the sum of the parts of a whole line of CD is CE plus ED is equal to CD. And that definition is by segment addition postulate. So now I have that CE is equal to CE plus ED is equal to CD. I want to take a look here in step two and see if there's anything I can do with some substitution. So if we take a look in step two for some of our substitution, this should be CE. This was a typo on my part. This should be CE is equal to FE. And ED is equal to EG. Now you should be able to tell that we are able to use some substitution, because CE is also equal to FE, and you notice that ED is also equal to EG. So in step four, I'm going to use substitution. and I'm going to say that FE plus EG is equal to CD, and that was by substitution. Okay, now we're ready for step 5. Step 5, so I've talked about my line segment CD, and now I'm ready to talk about line segment FG. So when I talk about line segment FG, I need to use this segment addition postulate again. And because of the segment addition postulate tells us that the whole line is equal to the sum of the parts. So I've talked about line segment CD. Now I want to talk about line segment FG. So in step 5, we get line segment FG is made up of the sum of the parts. So we have FE plus EG is equal to FG, and that is step 5. That is our segment addition postulate. Hey, now remember, I'm abbreviating on here. You are not allowed to abbreviate when you write your actual 2-column proofs on your homework, so make sure that you write out every step. Now hopefully you guys will see some kind of relationship here between our step 3 and step 4. We have FE plus EG in both spots. So hopefully you're able to tell, hey, now we see a substitution here. I can say now that CD is the same as FE plus EG. So step 6 says that CD by substitution is the same thing as FE plus EG, and it is equal to FG. And again in step 6, that was just substitution. And that came from our step 4. Now we're close to being done, but I need to talk about line segments. Okay, we're not talking about distances, so line segments. So I need to use that definition of congruency again to say that CD is congruent to line segment FG, and that is definition of congruency. So those are our 7 steps on how to prove, okay, that our CD is congruent to FG. So we always start out with a given. Then we use definition of congruency because I want to talk about actual lengths of measures. I don't want to talk about segments. Then I use segment addition postulate because I needed to add them together twice. Use a little bit of substitution and the definition of congruency once again. So then we get into properties of segment congruence. You have seen this many times. Okay, we're going to see it again as we get into 2.7. The reflexive, the symmetric, and the transitive property. The reflexive property says that line segment AB is going to be congruent to line segment AB. So the symmetric property, now we're going to have 2 different line segments. The reflexive is reflexive, it's equal to itself. The symmetric is going to say that line segment AB is congruent to line segment CD. Then we are able to conclude that CD is congruent to line segment AB. That is the symmetric property. And then finally the transitive. Okay, we use the transitive a lot. That says that line segment AB is congruent to line segment CD. And we know that line segment CD is congruent to line segment EF. Then we are able to conclude that line segment AB is going to be congruent to line segment EF. Right. So now we're ready for our last example. Our last example, it says X is the midpoint of SY and Z is the midpoint of YF, and XY is equal to YZ. So first let's draw it on our picture. We know that X is the midpoint of SY. So I know that SX has to be congruent to XY because it's the midpoint. I also know that YZ has to be congruent to ZF because Z is the midpoint. So those 2 distances must be congruent. And then we also know that our distance from X to Y is going to be the same distance as the distance from y to z. So those are some informations that we know, and we are trying to prove that ZF is congruent to SX. So when you start a two-column proof, just like we always do, we have our T-chart, we have our statements, we have our reasons. And step one is always the given. Okay, step one is always the given. And our given information is right here. Okay, I'm not going to rewrite it. Your given information goes right there. So then we're going to go to step two. And in step two, what I want to do is I want to talk about the relationships that we drew in our picture. These congruencies that we drew in our picture. So in step two, we're going to talk about SX and XY. As you can see, we said they are congruent. So we're going to say that SX is congruent to our line segment XY. And our line segment YZ is going to be congruent to my line segment ZF. And that is by definition of a midpoint. So when you have a midpoint, what you're able to determine is we're able to say, hey, since I have this midpoint, I know that the distance from S to X must be equal to the distance from X to Y. That allows me to be able to say that those are congruent. Those two line segments are congruent. Now I want to talk about the entire thing being congruent. So I need to take a look and change this distance right here, XY is equal to YZ, into a statement of congruence. The way we use that is definition of congruency. So in step 3, we're going to use definition of congruency. So it's going to change our equal sign into an XY equals YZ. So in step 3, we're going to have line segment XY is going to be congruent to line segment YZ, and that is by definition of congruence. Okay, then we take a look, hopefully maybe we can see some substitution here. If we take a look at our previous step, we see some substitution. We see that SX is congruent to XY. So we're going to substitute in step 4 SX in for XY. So now I can say that SX is congruent to YZ, and that is by substitution. Then also in that same step, you should be able to see that when we take a look at YZ, YZ is the same as ZF. So we can substitute in ZF for YZ. So step 5 allows me to say that SX is congruent to ZF. And again, step 5, that is substitution. Our substitution property. Now we're close to being done, but my answer, I wanted my answer here to be in this F or ZF is congruent to SX. So we have to use our reflexive property, which means that we need to flip it. So when I flip it, I'm going to end up with, and finally in step 6, I'm going to end up with ZF is congruent to line segment SX. And that is by the symmetric property. So remember on this that I went ahead and I abbreviated for some space. Make sure when you write your two-column proofs out that you do not use any abbreviations. In this, make sure you understand how to use the definition of congruency. That will be important as we move forward here. And that is lesson 2.7, proving